Okay. All right, I'm gonna start. Okay. All right. So this is a problem where they give you a moment. They give you the centroid here. Okay. So they give you the centroid of this figure already, so you don't have to calculate it. And they give you this moment. It's off at a 15-degree angle. All right. So what you have to do is break up this moment into its z and y components. So what's the moment around the z-axis? What's mz? It's 25 times the cosine of 15. Yeah, you're right. So what's my? It's 25 times the sine of 15. Okay, so I'll give you these values. My is 6.47 kilonewton times a meter. Mz is 24.15 kilonewton times a meter. Okay. All right. So now we have the components, the moments around the z-axis and y-axis. Okay, that's great. So which direction is it? So now I'm going to erase this instead of redrawing it. So now we have it in terms of its components. They're asking in this problem to find the stress at A, B, and D. Okay? So you have the moment around the z-axis is this way. So mz is equal to 24.15 kilonewtons times a meter. And then you have my, which is this way. So my is equal to 6.47 kilonewtons times a meter. Okay. All right. So we're going to have to obviously find the stress at A, B, and D because the problem's asking you to do that. So we have to find the moment of inertia of this whole thing, right? If this is the centroid, how are we going to find the moment of inertia? Right? They give you all these dimensions. I'm going to ask you guys. All right? You could break this up into two figures, of course. You could break it over here. So you have two rectangles. I'll call this 1 and 2. Right? And this is the centroid over here. So what's I1? It's 112 times B. B in this case is, first we're going to find the moment of inertia around the z-axis. Right? Because you're going to have two moment of inertias. One around the x, one around the z, one around the y. Okay, so I'll call this z1. Okay, so z1 is 112. B in this case is 30 plus 30 plus 30, which is 90. What's h? 80 exactly. Just want to see if you guys are paying attention. So cubed, and then area plus 90 times 80 times d squared. So what's d squared in this case? You guys know? It's just 20, yeah. Okay, so half of 80 is 40. So you have 40 minus 20 is 20. So it's this distance here. Okay. All right. So IZ1 is equal to, let me just give you the value for that. Okay, it's 6.72 times 10 to the 6 millimeters to the 4. Okay? All right, and now what's IZ2? IZ2 is equal to 112. B in this case is what?
30.
30 exactly. What is H? 80 cubed. Okay, and plus the area, which is 30 times 80. And the distance in this case is what? What's D? 60. It's measured from the centroid. So what is that? It's 20 plus half of 80, which is 60, yes. 60 squared. Okay. So IZ2 is equal to 9.92 times 10 to the 6 millimeters to the 4th, right? Okay, so you want the total moment of inertia around the z-axis. So it's just IZ1 plus IZ2. So IZ total is equal to IZ1 plus IZ2. So the total is 16.64 times 10 to the 6 millimeters to the 4th. Okay, that's great. Okay. All right, so now we also have to find the moment of inertia around the y-axis. So let's do that. I'm just going to write it here. Can I erase this? Yes? You guys got it? It's going to be in the video anyways. Okay, so now I want to find the moment of inertia around the y-axis. So let's find I1y. What is that? I'll ask you guys. It's 112, right? This is a centroid over here. So what is it? This is rectangle 1. It's 112 times 80, exactly. 80 is the base in this case. So 80. And what's h? 90. Exactly. Cubed. All right, so this is your moment of inertia right here. So this is equal to, let me go back. This is 4.86 times 10 to the 6 millimeters to the 4th. Okay.
Okay, so what did we calculate before? The I21, I22.
Oh, no, that was z. It was z1 and z2. That's the moment of inertia around the z-axis.
Okay.
You're going to need it. There's going to be, it's bending around the z and the y-axis. So you have to calculate the moment of inertia for both the z and the y-axis. Okay. So I2y is equal to 112. B in this case is 80. Whoops. And h in this case is 30. Cubed. Okay. So the value you get for that is 1.8 times 10 to the 5th millimeters to the 4th. All right, so you need the total moment of inertia around the y-axis. So I-y total is equal to, just add these two, sum them. So you get 5.04 times 10 to the 6 millimeters to the 4th. Okay. All right, so you got the total moment of inertia around the z-axis and the y-axis. Now we can find the stress, okay? We could find the stress at point A, B, and D. So let's do that. Okay, so I'll ask you guys, what's sigma A? What's the stress? There's no force, it's just, there's moments, okay? So there's going to be stress due to bending. There's going to be bending along the z-axis and the y-axis. So what's your stress? And be careful, right? This moment is going, clockwise. So this point over here, if you find the bending stress due to the moment around the z-axis, what is that going to be? At point A. Point A is going to be in compression, right? Yeah, exactly. So it's minus mz, okay, and the distance is what? It's just this distance over here. I'll call this ya, yeah, which is 60, you're right, okay? This is ya over iz, total, okay? And there's also going to be a moment around the y-axis, which is going to cause what? Tension or compression at point A?
Compression.
Compression. It's going this way. It's tension. It's being pulled. Do you see that? Okay. So plus my za over I y total. Okay. All right. So this is a formula. So all you need to understand is whether it's compression or tension. Anyone could write this down, but you just need to know the signs in front. That could totally change your answer. So that's important, right? Okay. So that's all I want you really to understand from this lecture, because this whole lecture is the same thing over and over. So since this is being bent clockwise, you can see this part is going to be in compression from MZ, and from MY it's being pulled away, so it's going to be in tension from MY. So that's why we have the plus here, that's why we have the minus over here. Alright, so after you plug in the values, so we know this is equal to 24, you let me just write it instead of just, okay. So this is 24.15 kilonewton times a meter, right? And you guys are going to convert that for yourself. Okay, so YA in this case, oh, and this is ZA, ready? It's from here to here, so this is ZA. Okay, so we know YA, like we said before, it's 60, it's a distance from here to here, so that's 60 millimeters over the total moment of inertia. I erased it around the z-axis. Is
16.64 times 10 to the 6.
Yeah, you're right. 16.64 times 10 to the 6 millimeters to the 4th. And just make sure you convert this. You can't, obviously you can't just multiply this out and divide it. You're not going to get the right answer. Okay, and then you have plus this term, which is my is 6.47 kilonewton times a meter. The distance z is ZA is what? It's just half of this distance. It's 90 divided by 2, right? Okay, so it's 45. 45 millimeters all over the total moment of inertia, which is 5.04 times 10 to the 6 millimeters to the 4th. Okay? Alright, so the stress at A is equal to minus 29.3 MPa. Alright, so that's the stress at A. Likewise, we can get the stress at B. But this time, I'm not going to give you the formula. I'm going to ask you guys to give me the formula. Okay, so what's the stress at B? I'll let you guys try. So this moment over here, My is causing B to be in compression or tension?
Compression.
Compression, exactly. So it's minus My. The distance over here is, I'll call it ZB. This is ZB. Okay, so it's My ZB over the total moment of inertia around the y-axis. And then you also have this moment is going clockwise, so it's going to cause B to be in compression or tension. Compression, exactly. They're both minus. So it's MZ. The distance in this case is still, it's YB, which is the same value as before. YB over IZ total. Okay, and I'll just plug in the values now. Okay, so it's minus 6.47 kilonewton times a meter multiplied by the distance z, which is 45 millimeters all over. Oh yeah, that's right. But I was just checking. 5.04 times 10 to the 6 millimeters to the 4th. And then you have minus 24.15 kilonewton times a meter multiplied by 60 millimeters all over the total moment of inertia, which is 16.64 times 10 to the 6 millimeters to the 4th. Okay, so the stress at B you get is minus 144.8 MPa. Alright, and then finally they want you to calculate the stress at point D. So that's the stress at point B, and we would expect it to be in compression, that's why it has a minus sign. Any questions? It was pretty easy. So like before, it's the same thing, except now you have to find the moment of inertia around two axes, maybe the y and the z or y and x, whatever they give you in the problem. And you're going to have two stresses due to bending. Okay. All right, so what's sigma d? I'm not going to help you this time. I'll ask you. So for what about the bending around the z-axis? Is it positive or negative?
Positive.
Positive, exactly, yeah. So it's mz, the distance here, I'll call it zd. No, yd, yeah, sorry, yd. And what is that? It's just 80 plus 20, so it's 100 millimeters. yd. All over the total moment of inertia around the z-axis. And then what about the y? Is it in compression or tangent? Compression, exactly. So it's minus my, distance is z, zd. And what is that? It's just half of 30, so it's 15 millimeters. Zd all over Iyt. Sorry for the squeaking. Alright, so sigma d is equal to, let me just fill in the values, minus 6.47. Multiply. Yes.
Why is first over IZT and another one over IYT?
Oh, because this is the total moment of inertia around the z-axis. You're finding the bending stress due to the moment around the z-axis. So you have to use the moment of inertia around the z-axis, the total. So you could look at this term, and you know this has to be on the bottom, right? It's always a total moment of inertia. That's why I have the moment of inertia on the bottom. This is the formula for bending stress. Okay. Okay. This is 15 millimeters. Oh no, I have it backwards. I have to give you the positive term first. This is 24.15 kilonewton times a meter. The distance is 100 millimeters over 16.64 times 10 to the 6 millimeters to the 4. Okay, and then you have this term's positive, this term's negative here. It's 6.47 kilonewton times a meter multiplied by the distance, in this case is 15 millimeters over the total moment of inertia, which is 5.04 times 10 to the 6 millimeters to the 4. Okay, so the stress at D is equal to 125.9 MPa. Okay. Any questions?
Yeah, does the problem give you a distance from D to the y-axis 20 as you wrote there, or?
Yeah, this is 20. You
No,
mean?
I mean on the bottom, like from D to the y-axis.
ZD.
Yeah.
Oh,
that's
this distance,
okay.
yeah, this is
I
30.
thought that was 20.
Oh,
Instead of CD, okay.
No, yeah, this distance is 30, so half this distance is 15, and this is 15.
Yeah, but I confused the ZD by 20.
Oh, yeah, they give you this distance on the problem, 20. The only reason why they give you this distance is so you could find the center of this rectangle, 1.
He means
for
the
I1.
ZD on the bottom, those are the 20.
It looks like you wrote 20.
Oh, this looks like
Yeah,
a 20. Oh, this
that's
is ZD. This is a D. Sorry. Yeah, this is equal to 15. Sorry. Okay. Okay, this is 144. Okay, so let me draw the picture for you guys. Picture's gonna be point's A, this point's B, and this point is D. What else do they give you? They give you the thickness of the wall. Okay, so they give you T, I'll just call it T in this case. They say T is equal to 12 millimeters. Alright, and they give you obviously these distances. Okay, this is 75 millimeters, and this distance from here to here is 125 millimeters. Do you guys, can you see from my drawing which dimension's which? Maybe I should just draw it here. Okay, so this is 75 millimeters, and this is 125 millimeters. This distance over here, from here to here. Okay. So they give you all that stuff, and they ask you to calculate the stress at A and B. Okay, so they want the stress over here and over here. And then, okay, yeah. So we're gonna have to find, obviously, the moment around, let's draw an axis so we see what's going on. So I'll call this out of the board is X, up is Y, and to the left is Z. Alright, you guys follow? Obviously this is the centroid of this thing, it's right in the middle. So I'll call this C even though the problem doesn't give it to you. Alright, so let's find the moment around the Y-axis and the Z-axis. Alright, so what's the moment around, I don't know, the Z-axis? What is it? Right? It's this distance is 125, so it's 125 over 2. That's the distance. This is in millimeters. Maybe I should write that down. Okay, so that's this distance from here to here, and then it's actually from here to here multiplied by the force, which is 14 kilonewtons, and that's going clockwise. So is that minus or plus? Minus. It's minus, exactly. All right, so that's not it. Obviously, there's others. There's two forces over here that are going to cause a moment around the z-axis. So it's also the distances are the same, but these are going to make it rotate counterclockwise. So these are both positive. So it's plus. The distance is the same, so it's 125 over 2 millimeters multiplied by 28 kilonewtons. And then there's another one, plus 125 over 2 millimeters multiplied by 28 kilonewtons. Okay? Alright, so the moment around the z-axis,
Wait, where's T?
T?
T.
T is just the thickness of the wall. It's 12 in this direction and 12 in the y direction, 12 in the z direction. So this is 2,625 Newton meters. And this is the direction counterclockwise, because you get a positive value, so that indicates it's counterclockwise. Alright, and we also need the moment around the y-axis, and what is that? Right, you need this distance from here to here, right, multiplied by this force, and then multiplied by this force. So you have, that distance was 75. So 75 over 2, right, millimeters, multiplied by 28. Is that positive or negative?
One positive, one negative.
Huh?
One positive, one negative. Or so we have 228.
This is it, now we're taking the moment around the y-axis, so it's going clockwise. You see that?
Yeah.
This distance times this force will make it go clockwise, so it's minus, right? Oh, I'm talking about this 28, not the one. Oh, okay. Yeah, all right, you're right. You're talking about this one?
Yeah.
Okay, so sorry, that was my mistake. All right, so I'm going to do this 28 first. So it's minus. And then you have plus, they're going to cancel out. You notice they cancel out. So you have this distance from here to here, which is just half of 75 multiplied by 28. So it's plus 75 over 2 millimeters multiplied by, I'm going to get another piece of chalk. 28. Sorry, I gotta learn how to not make this chalk squeak. Okay. Alright, so these cancel, and then you have one more force. So you have this distance times this force. So that's gonna be minus 75 over 2 millimeters multiplied by, the force is 14 kilonewtons. Okay, so my is equal to 525 Newton meters. You get a negative value, so that indicates it's going clockwise. Alright, so you have a moment, my is going clockwise, so it's this way. And then you have a moment around the z-axis, which is going counterclockwise, so it's going this way. Okay. Let me draw this right. You can't even see it. This is going this way. Okay. So this is my and this is mz. Alright, so now that you have the moments, you're going to obviously have to calculate the moment of inertia. The moment of inertia is pretty easy to calculate in this problem. And remember, do we have to calculate it, the moment of inertia around the z-axis and y-axis?
No, they're the same.
Huh?
Are they going to be the same?
No. They're not.
Why not?
They're not, because look, when you calculate the moment around the y-axis, your h and b change, right? If these dimensions were the same, then you wouldn't. Yeah, if it was a square, the way I drew it was a square, but it's actually a rectangle. So yeah, you do have to. So. Yeah, if it was a square, you're right. You don't have to. You could just calculate it for one, and then you'll be good. Okay. All right. So you need to calculate the moment of inertia around the y.
There you go.
All right. So okay. All right. So it's 112 times this distance, which is 125, multiplied by this distance, which is 75. Minus, all right, you're subtracting out this part right now, this little rectangle. So it's minus, this distance now is what is this distance over here and this distance over here? It's 125 minus 24, so it's 101. This is 101, and this distance is 75 minus 24. What is that? That's 51, right? Yeah. Okay. All right, so subtract it out. You have 101 multiplied by 51 cubed. Okay, so that's your total moment of inertia around the y-axis, and around the z-axis is 112 times, okay, we got 75 multiplied by 125 cubed minus, what do we have now, 51 multiplied by 101 cubed, okay? So Iy is equal to, and Iz is equal to, okay, so Iz is equal to 7.828 times 10 to the 6 millimeters to the 4th, and Iy, where is it? On this page. This is equal to 3.278 times 10 to the 6 millimeters to the 4th. Okay, so we got the total moment of inertia around the y-axis and the z-axis. We calculated the moments. What's next? Now we just have to find, we also, okay, so let's draw a free body diagram of A, B, D. Because we have a stress due to bending around the z-axis, the y-axis, but we also have the stress. This is going to be in tension, right? There's forces here, here, and here. So the net force is just 28 plus 14, which is 70. Okay, so this thing's going to be in tension too. So you have a P over A term also. So let's draw a free body diagram of this part A. We're gonna cut it at A, B, D. So because we want to know what's happening at that cross section. All right. So if we draw a free body diagram of that, we got this cross section. Okay, so this is A, B, and this is D, right? All right, so what's the total force? I said this is going to be in tension. If you cut it over here, the force is going to be pointing in this direction, but you have an equal and opposite force pointing in the opposite direction. So I'm drawing just this part. If I cut it over here, I'm just drawing this part from here to here. So the force is going to be to the right. So this is 70 kilonewtons. Right? And you're going to also have, let's draw the axes. This is Z, and this is Y. And this is the x-axis, but it doesn't matter. All right, so we calculated the moment around the z-axis. It was this way. It was counterclockwise, so mz, remind me what mz was.
2,625 newton meters.
Okay, and what about my?
Negative 525 newton meters.
Okay, so this indicates it was clockwise, so it's this way. So this is my. Okay, and this is mz, right? So that's a complete free body diagram of A, B, D, right? And now we want to find the stress at point A and B. So this was A and this was B. A and B. Okay. All right. So let's just first calculate the stress at A. Oh, we're gonna also need something else too. All right. Let me just write down the formula first. All right. The stress at A is equal to. Remember, we have a force in this problem. So it's going to be P over A. Is this positive or negative, this term?
Positive.
It's positive, exactly. This is being pulled in tension. So it's positive. All right, so we're figuring out the stress at A. So what about the moment around the y-axis? Is it causing this point A to be in compression or tension?
Tension.
Tension.
Pressure.
Yeah, that's the only other choice. You see my, it's going clockwise. So this point over here is going to be in compression, right? Yeah, if you're looking at mz, it's in tension. So so my is minus my. The distance in this case is what? It's just this distance from here to here. So it's just half of 75. I'll just call that ZA. Okay, so ZA over the moment of inertia around the y-axis. I erased that before. And we have another term from, there's a moment around the z-axis, so it's plus. Remember, this is in tension because it's going counterclockwise. So it's plus mz, the distance in this case is ya, over iz. Okay? And we calculated this. We know this, ya is half of 125. So it's 125 over 2, and ZA is equal to 75 over 2. Okay, and we have to calculate the area, the cross-sectional area too. That's the only term we're missing. So what's A in this case? A, this is just a rectangle, so it's 125 times 75. 125 times 75, and then you have to subtract out the hollow section, so it's minus 51 times 101. Okay, so the cross-sectional area is, it's right over here. It's 4.224 times 10 to the negative 3 meters squared. Okay. Alright, so this is in millimeters. You'll get it in millimeters, and then you can divide by 1,000 squared to get in meters squared. Okay, so now we have everything. We know P, we know M. You have to plug everything in, or I could just give you the solution. Do you want me to plug it?
Well, when you plug it in, do you use, I mean, you choose the stress based on the direction of the movement, correct? So,
Yeah.
Okay, so what I did for the homework was I drew two separate figures, and I drew say the moment around the z-axis, and I drew say the top of the compression, the bottom of the tension. Is that how you go about it?
No. Well, when I solve these problems, I just look. I draw the free body diagram, and I look. A lot of the times, what the book does is they say, oh, this distance is negative, and this is negative, so it's going to be positive. But then you get confused. If you just think about whether, intuitively, you know this is going to be in tension due to the moment around the z-axis because it's getting pulled, and you see this moment is going to cause it to be in compression. You see that? So if you think of it that way, you can never get these signs wrong. Because these signs are going to give you they're either going to kill you or make you, on an exam. If you did have this problem on the exam, these signs are important. So you have to know the sign over here, the sign over here, and the sign over here. And you could just get them just by looking at the free body diagram or the picture.
Okay, but when you plug in for my, I know it was counterclockwise based on that you got it was negative. So would you just plug in 525 for my?
525.
Newton meters.
Oh, you're talking about the moment.
Yeah.
Yeah, you could plug in for my. Oh, you mean minus? No, because then this is going to say it's in compression there. You see? And it's not in compression. But if you want to do that, if you want to plug in minus 525, then the distance has to be negative. So
Okay.
YA has to be negative. And MZ, okay, so YA is negative though. So if you want to do it that way, a minus and a minus, this distance is below the z-axis, so it's minus. It's minus 125 over 2. So yeah, minus and a minus. But if you might get caught up in that, and you might make a mistake on the exam. I think it's easier just to see that this moment is going to cause it to be in tension, and this one's going to make it in compression.
Okay, yeah, that's how I do it.
Yeah.
So just to make sure, on the middle equation we would plug in plus 525.
Plus 525. Yeah, you're right. Yeah.
Okay. So we're just going to do basically the absolute value and then we put this.
Yeah, exactly.
Okay.
Yeah, take the absolute value of the moment. You know the direction. So yeah, you get minus, but that indicates that it's going clockwise. So you could just say this is 525 Newton meters clockwise, right? So you know the direction. So you draw the free body diagram, and then you can determine what these bending stresses are going to do to point A and point B. Right? Okay, so I'm just going to give you the value. So sigma A is equal to 31.5 MPa, right? And then you have to calculate the moment, the stress at B. All right, so let me erase this. Okay, so what's the stress at B? I'll just write down the formula and then we'll just wrap it up. I'll write down the formula and I'll give you the answer, but I want you guys to try since we have like 5 minutes. So what's the stress at B in this case? P over A is plus or minus. It's positive, it's still in tension. So it's P over A, that term always stays the same. So now how about the moment around the y-axis? Where we're looking at point B. Is it going to be in compression or tension? Compression, exactly. So it's minus my zb over iy. And then what about for mz? It's in compression again. So it's minus mz yb over iz. Okay? So we know these values, yb and zb, okay? You guys can find it. Yb is, it's just 125. This is equal to 125 over 2. This is equal to 75 over 2. We found the moments. You plug them in. So the stress you get is equal to minus 10.4 MPa. Okay. So that's it. These problems are too long. I couldn't get them long. I don't feel too long. Any questions? Thank you.